The homework will be posted today. Sorry for the delay on that. Jamie, is there any other things that we should announce today?
Nothing I can think of immediately. Reminder that, just in general, please mark the problems when you're submitting things to Gradescope, or we reserve the right to take off points. That helps with people's ability to grade. I think that's everything I can think of. Oh, no, that's not true. We have mid-quarter evaluations we'd like you to fill out. Please check Piazza after class for details on that.
Great. Okay, without further ado. Okay, so I'd like everyone to take a moment and take a look at this example I have for you here. Sorry, and these are uploaded to the website now. Wow, that would be really bad. Sorry, I was having some AirPlay issues in setting up. There we go. Thank God. Sorry, I changed my setup this morning and it was really a bad idea. Okay. All right, so everyone take a moment and take a look at this slide. This is going to look familiar to some of you that were doing, well, it'll look familiar to all of you based on homework 1. But what I want to focus on, this lecture that I'm going to give today is all about computation. It's about how do we optimize functions efficiently in convex optimization. And what I want you to think about with this exercise is just to think about like how, what's actually being done in the computer, what's actually being done behind the scenes, how much memory is being used, how much computation is being used within the computer, each iteration to solve this sort of thing. So I just want to walk through, so just take like 30 seconds and sort of read this code. What's going on here is that we have this piece here. This is generating some fake data. I'm generating some random features. I'm just some transformations, some feature maps. And then I'm doing each one of these branches, the blue, the red, and the green are 3 different ways you can each do an identical computation. These are all computationally identical. You get the result out at the end of the day. And then we're solving for our least squares estimator. W is equal to H transpose H plus lambda times identity. So this is our ridge regression. And then H transpose Y. And so what each of these blue, red, and green boxes are doing are computing H transpose H and H transpose Y. And they're doing this in different ways that trade off memory and computation. And so just take 30 seconds and just read each one and try to think about what it's doing. And then we'll come back and discuss it for a few seconds. And then we'll return to this slide at the end of today's lecture and discuss some additional trade-offs. Oh, where are these slides uploaded? Did I not upload? Oh, I didn't change the HTML. Okay, I'll just put it in the chat, the direct PDF, but it's.
And I'll update the HTML 1 second.
Oh, thank you. Let me, let me push. So you got the latest, but In the chat, I just posted the direct link to the PDF. Sorry, I didn't change the HTML, and I don't trust myself to do it live right now.
But I can, because I'm not online.
Okay, so let's talk about this. So what this is doing, just some operations. And by the way, you should also see this should be cosine, cosine. And so each one of these things, basically you're transforming xi into cosine of G transpose Gj transpose xi plus Bj. Right? This is our sort of random transformation. We looked at a couple of these when we started talking about feature maps, but this is just one of them that we could do. It's just creating nonlinear versions of our features. And then so if x is equal to x1, xn, h is then going to be equal to h1, hn, where this is in R n by D, and this is in R n by P. And so what I want to do first is this green, what I want to look at first is this green one, which is the most direct computation that you would do. This is what you would do if you're trying to maximize using inner products or matrix multiplies. And this is just using NumPy's matrix multiplies, and this is going to be the fastest one because you're taking advantage of all the matrix multiplication optimizations that NumPy and LAPACK and BLAS and all of these linear algebra libraries behind the scenes can use and exploit. That's one extreme. The blue, on the other hand, is the other extreme. The blue is sort of the naive sort of implementation where you are building up H transpose H through a for loop. Because H transpose H is also just I equals 1 to n of hi transpose, and hi is the vectors, and it's just building that up one at a time, one vector at a time. And so this is going to be, this is storing only ever H transpose H, which is going to get P by P matrix. But now if we look at, if we instantiate H first on this right-hand side again, comparing to the green, this is going to be a n by P matrix, and then a P by P matrix. But on this hand, the biggest thing we ever allocate is P by P. So we never allocate n by P. And so if n is very, very large, this could be very, very difficult. And because all this is ever using is in memory X, which is n by P, or sorry, n by D. And so the total amount of memory on this side is going to be nd plus P squared. Whereas if we do the green, we're doing something like nd plus np plus P squared. And so if n is very, very large and P is very, very large, the green could be much less memory efficient. I mean, it could require a lot more memory, but it is much faster because it's taking advantage of matrix multiplies through NumPy. And so these kind of trade-offs of memory versus how much memory it's using versus how much computational savings you're getting and efficiency is what we're basically going to be talking about today. This is a pretty simple case, but I wanted you to see it, and so you can see these sort of trade-offs and think about when you're implementing something, how you implement it is really important. The blue is sort of a trivial sort of, or sort of a naive or straightforward application of computing H transpose H in inversion. And so this is the solution to the homework problem, homework 1, that last one using those random features. In the red, I'll let you look at this offline, is basically some, it's some sort of like middle ground between these two extremes, and it gets basically the best of both worlds. Yeah. And so I don't want to stress this, but like just take, you should look at this stuff offline and try to convince yourself that this is really skating this line of computation versus memory, and there are more efficient ways to program things. Okay, so any questions on this or the class before we get started?
There seems to be a question in the chat about what P is.
P is the dimension of the number of random features that we build. So J runs from 1 ... to P. So we generated P new features from our D original features. Okay.
I have a basic question in terms of computation and memory. So I get the computation part, but in terms of like holding memory, like what exactly are you holding? This is like a super basic CS question probably, but like what do you mean by like memory itself? Like, are you storing something? Aren't you at the end, aren't you going to be storing P by P things anyway?
Real numbers. So like whenever the note, usually we think of as any real number that you're putting into NumPy, it's going to be stored as a float, which is a double, is 8 bytes. Mm-hmm. And that's what we're worried about here. And really, you're always going to be storing P squared things here in this computation, but you can get down to N times P. But the green uses N times P, and if N is very large, then N times P can be much larger than P squared. And so you're just trying to avoid that. And what we're going to see at the end of this lecture is that you can actually solve this problem in N times D plus P, and never actually have to do this P squared thing. And that's what we're going to get to by the end of this lecture. Okay, how do we do that? So, but to get there, we need to talk about convexity. Jamie started talking about this yesterday, or on Monday, and I'm just going to review it because it's such a fundamental thing that we'd like you to really have some intuition for, but also analysis capabilities as well. So I'm going to briefly go through some basic definitions and very, very quickly review gradient descent that Jamie went through, and then we'll move on to more advanced topics. So one thing when I started learning about convexity, there was this confusing notion of what is the relationship between a convex set and a convex function. And so we're going to go through some basic definitions and analysis in the first few minutes here. So we say if a set K in RD is convex if for any convex combination of two elements within K, that the convex combination of those two elements is within K itself. So the picture here is if you have X here and Y here, then for any lambda between 0 and 1, that basically defines this line that is between them. And so a set is convex if for any xy that is in K, the convex combination for any lambda 1 minus lambda x plus lambda y is also within K. Okay, and so as you can see, you can always draw pictures. I strongly encourage you to do that. If you do that, you'll, for any 2 points, they're all, any chord you can draw within this set will lie within this set completely. The set does not need to be compact. You can have a set be infinite. So like this is the line that's like, this is just a set that's infinite going up in the upper right corner. And this is also true for this set here. And so if I have a point like at infinity, then like this is also a convex set. Okay, what are not convex sets? Here are some, basically anything else. Anything that is not convex is non-convex. And so simple examples here. This is not convex because when I draw this chord between any 2 points, x and y, this point, all these points here are not in K, and therefore it cannot be convex. Again here, again here. And so we'll be asking you on the homework, what are convex and convex sets? And we'll be basically saying, please, say whether these sets are convex or whether they're not convex. And then for specific convex sets, we'll ask you to actually prove that a set is convex. And so these are concepts that you'll need to know. Any questions on convex sets?
Yeah. How do you prove a set is convex without a fun picture?
So how you get, so basically you need to have a parametric form for the set. So if I said that, so if my set K is equal to x, y, such that x squared plus y squared is less than or equal to 10, then you would need to be able to prove that that function is convex. And the way that, or that set is convex. And the way that you would do that is for any, maybe not that way, x1, x2, x2. And then so what you would do is you would try to plug in for some x1, y1, x1, x2, y1, y2 in K. So you assume that those 2 points are in K, and then you define this convex combination for any lambda, and you prove that that convex combination is in, and show that 1 minus lambda x1 plus 1 plus lambda x2, 1 minus lambda y1 plus y1 x2 lambda y2. Yeah. Show that this is in K just using the definition of K.
Yeah, and if we're talking about not a set, but the set defined as sort of the upper envelope of a function, right? Which is, or sorry, the space above a function, which is what we were talking about convexity to mean in the last lecture, and I'm sure that's what Kevin's going to go to talk to in a minute. Usually that has to do, you can do some calculus to prove it, right? So
Yeah.
we gave you some different definitions of convexity that have to do with gradients, and that's often the way that you'll prove convexity for that particular case.
Yep. As Jamie was alluding to, we have convex functions. And so what is so we just have a convex sets. Now let's talk about convex functions. And then in the next slide, we'll talk about how these two things relate to each other at all. So we say a function is convex if the convex combination of any 2 points x, y in the domain of f, and lambda in 0, 1 is lying below the line. So for any 2 points, this is x, y, this is f of x, f of y, then the line that connects these, two is lying above the curve, right? It's lying above this guy. Oop, that's not right. The orange is that. And so we define that this, now we have any 2 points on the function, the chord that connects the chord that connects those 2 points x and y, f of x and f of y, has to lie above the function f of z for any z between x and y. Okay, and again, this is sort of proven by picture. Any 2 points x and y, it will lie above the line. And again, we have that, these functions can go off to infinity. And what's important here, which is a typo, is that it's for x and y in the domain of f. In the domain of f is the set x such that f of x, it's not really the domain of f, where f of x is defined. Let's say that. So like, for instance, 1 over x is not, usually you define the domain of f on just the positive real numbers, because otherwise it would go off to infinity or be negative, and it may not be what you're actually interested in. So like maybe you're interested in probabilities, and so all you'd really care about is between 0 and 1, things like this.
One other comment. If we have a strictly increasing function like the exponential function, right? That's also going to satisfy the definition of convexity. It doesn't quite look like a bowl. It looks like, I think the point is you can have a strictly increasing function, which is also convex. And I just don't, I would imagine like if you're always thinking that it has to have 2 walls going upwards, that's not quite right.
That's right. It can go up to infinity, like e to the x, and then this would be e to the minus x. This would be, say, x squared minus x. These things can go up to infinity, and this is some piecewise linear function. And so with a non-convex function, anything else. So right here, this violates it, right? This is right there is proof of non-convex. And so on the homework and things like this, we'll be asking you to sort of like say what functions are convex, non-convex, and then ask you, give me an example. When I say, give me an example of why this function is, or tell me why this function, either prove it is convex or show that it's not convex. And to prove that a function is not convex, you only need to find one example that is not convex. And finding any 2 points like this would suffice for that purpose. Okay. And so these are convex functions, and the connection between convex sets and convex functions is the following, is this purple definition here. A function f is convex if the set x and t, so x is an RD, and t is some additional real number, the set xt such that f of x less than or equal to t is convex, okay? And so what is that? So like let's just pick one particular t. So let's say like t prime. Then this set x xt such that f of x is less than or equal to t prime is going to be this set right here. And what this set is doing is basically all points t, all points x and t, such that f of x is less than or equal to t. And so what this set is, it's this entire function like this. And what we call this has a very special name. This set here is called the epigraph of f. And so basically, we say that a function f is convex if its epigraph is a convex set. And so this is the connection between convexity, convex set, and convex functions. These are equivalent definitions. You can the purple and the green are totally equivalent function sets. You can go back and forth between these two, and you're welcome to try to prove that these are if and only if. And so this is these are definitions of like what convex is and how just looking at a function whether you can be confident with whether it is convex or not. Okay, before getting into how we would actually prove these things, do you have any questions on this?
Yeah, I just have a clarification question. Can you explain the d plus 1, how that works for this example?
Yes. So here, this is our x, and then here's our f of x. The y-axis is the f of x, and the x-axis is the x. And so here, our d is equal to 1, because we're only in our x variables are only one-dimensional. And so when I think about the set x, the epigraph of f, that's xt in the dimension of your input variable x plus 1, because now you're actually looking at the f of x variable as well. And so in this case, this set is in 2 dimensions. The epigraph of f, this set here, is in 2 dimensions because it's all points that are lying basically above the function f. And so instead of thinking, so you're traditionally thinking of functions as a function of d, but then you can also think of like, well, that is actually just, if you sort of lift it, you look at the broader sort of like, what is it regressing to, that as a d plus 1 dimensional object. And so that's what it's doing.
Got it. Cool. Thanks.
Okay, so these are definitions, not the easiest things to work with. How do you recognize that a function is actually convex? And so one of the most common ones to determine whether a function is convex or not is this alternative definition, where if a convex f is differentiable everywhere, meaning it has a gradient defined everywhere, then we say it is convex if f of y is greater than or equal to f of x plus grad f y minus x for all xy. And so as Jamie went through this definition last time, and so basically what this is saying is that, or equivalent to saying in pictures, is that because this is grad f, x, and so what it's saying is essentially you can lower bound your function by a hyperplane, and a hyperplane is defined by the gradient of f. And so you just take the tangent line, and basically the function has, for any point x, the function has to live above that tangent line, and that's this gradient. And so sometimes if you have an analytic form of f, like f is equal to e to the x, you can prove using this method that it is convex. So like try at home for f of x equal to e to the x, or f of x equal to x squared, show convex using this definition. And so this is one way you could prove that f is convex. A third way, a third definition of convexity, sometimes the easiest one to prove, is that a function f is, so a twice differentiable function, meaning you can take 2 derivatives of it. Its second derivative is defined everywhere. In a higher dimension is known as the Hessian, and if the Hessian is defined everywhere, it's a matrix of partial derivatives, then the function f is convex if it's Hessian, where grad f of x, the matrix ij, is equal to df of x xi dxj. It's the derivative with respect to the ith coordinate and the jth coordinate. And so there's a matrix, and if it is this little symbol here means positive semi-definite, and so a is going to 0 if x transpose ax is greater or equal than 0 for all x. This is a definition. We'll get more into positive semi-definite in when we talk about covariance matrices and SGD and things like this. But for now, just take these as definitions because it's very useful. So as an example, basically it's saying that the curvature is positive everywhere. And that is very much the definition of like a bowl. So if f of x is equal to say 1/2 x squared, then f prime of x is equal to x, and f double prime of x is equal to 1. In this function, 1 is greater than 0 for all x, obviously. And so immediately we have that implies that f is convex in a very, very simple proof. Another one, e to the x. F of x equal to e to the x, f prime of x equal to e to the x, f double prime equal to e to the x. That was a particularly bad example, I'm realizing now. Well, this is always greater than 0 for all x, which implies that e to the x is convex. So like I said, this last definition is twice, if the second derivative is positive everywhere, is really often the easiest way to determine whether a function is convex or not, but it does require it to have two defined derivatives, which you may not have sometimes. The second derivative may blow up or just not be defined in a lot of places. Okay, any questions on these definitions? Because what we're gonna ask you on your homework we'll give you some functions and we'll ask you if they're convex or not, give you some sets as to if they're convex or not, and we'll ask you to prove that they're either convex or to give a counterexample where they're not convex. And these counterexamples literally can be as simple as drawing a picture and showing that the chord lies below the function. Okay. So any questions on that? Good. So, okay, that was like convex analysis 101. Believe it or not, there's an entire course given in electrical engineering that covers convex analysis for an entire quarter. This is basically day 1, and you can go much, much, much deeper and to prove all sorts of properties and facts about convex functions. But one of their biggest properties that we love a lot of convex functions is that all local minima are global minima. This means that any point that where the function is so a local minima is you're at a local minima if you look around you in every other direction, the gradient is going up or the function is increasing. Okay. So that's what a local minima is. In a local neighborhood, if x is a local minima, if I move in any other direction infinitesimally small, the function value increases. That's a local minima. And so for convex functions, every local minima is a global minima. For convex functions, that's not true. So these are local minima. But this is the global minimum. It is the only point that is the minimum of this function. And this actually comes in very handy, this property, and other properties of convexity when we come to building algorithms. So we like convexity because we can build algorithms like gradient descent or coordinate descent or any other kind of algorithms. And we can guarantee that if you just follow your nose, if you just sort of start here and move to the side, you will, with an appropriately tuned step size, the smaller step size, you will converge to a minima just by following the nose. Like you think of rolling a ball downhill, it will converge to a local minima. And if the function is convex, every local minima is a convex, is a global minima. You can stop searching. That is not true, say here, where if I roll the ball downhill, you might go into a global minima. And so depending on where you started, you might hit a local minima or a global minima. And so this is why we like convex functions. And so an important algorithm that Jamie talked about was gradient descent, which is just initialize your iterate at w0 or randomly. For convexity, this doesn't really matter that much, but you can still the initialization doesn't matter that much, but you want to keep it relatively small. And then you define some step size eta, and then you just go downhill, like I just did. And so for non-convex functions, you might run into local minima, whereas global minima are always true for convexity. One thing I wanted to mention, though, was subgradient descent. So Jamie mentioned this last time, but I just wanted to go over it again. Sorry. So if I had some function that had discontinuities in it, at this point, f is not differentiable. Right? Like for f of x equal to absolute value of x, f is not differentiable at x equals 0. The gradient doesn't exist. But we can still do something called subgradient descent, where a subgradient is any vector g such that at is a subgradient for location x if f of y is greater than f of x plus g transpose y minus x. Okay, if it just satisfies that. So if you look at you'll recall that so if f is differentiable at x, then g is equal to grad f of x. But when f is not differentiable at x, then you can find some other differentiable point. So for instance, but g in any point in negative 1, 1 is a subgradient for absolute value of x at 0, since y is greater than or equal to x plus g y minus x for any g in negative 1, 1. And I'd encourage you to check that. With a picture, basically any g, any of these red hyperplanes are supporting the function, and all those hyperplanes g are defined between negative 1 and 1. All of these are g prime, g double prime. And so subgradients, which brings us a good point, are not unique. Meaning at a point x, you may have multiple subgradients. There's not necessarily just one. If the function is differentiable, then it is unique at x, and it's just equal to the gradient of f. I guess the only one. But when you but at x equals 0 here, multiple g's can play the role of the subgradient, and it's not unique. And so if you want to do an algorithm for gradient descent, instead of using the gradient descent update with the gradient here, you use just any subgradient or any vector gt that satisfies the same equation that the derivative or the gradient of the convex function is satisfied. And we can do this. The final thing I just want to say is that non-convex functions, subgradients, do not necessarily exist. Necessarily exist for non-convex functions. And this is pretty immediate from the definition, right? There's just no, if I have a point here, and at that point, there's just no plane I can put under that will make the function be above it. And so for non-convex functions, subgradients don't always exist. However, convex functions have subgradients defined everywhere. Okay. And so this is just, it's a very technical thing. And subgradients seem just like, well, in some sense, they seem like duh, like, okay, I'll just find some subgradient. But there's a technical thing that needs to be sort of defined because you will run into issues where the gradient is not defined, and we need to deal with it. And everything sort of, as you might expect, goes through and it works. But this is how we think about it. And so this is subgradient descent. It works if your function is f is convex, then it will converge to a global minima. Another sort of in higher dimensions, what I wanted to mention is another algorithm, and another algorithm that relies heavily on convexity, which is coordinate descent. So if you have some function, a convex function, if I'm looking down on it, will look something like this. Right, so now I'm looking sort of like, you can think of this as looking down, like down onto the epigraphs from above. So now I have x1 and x2.
I think somebody is not on mute who maybe should be.
Okay. Oh, I just dropped my desk.
Could one of the TAs find that person and mute them, please? Thank you. And so what coordinate descent is doing is this is T mod n. So if n is D. So if I'm on iteration 30 and I'm in 2 dimensions, then 30 mod 2 is 0. We want to do +1 if I'm not doing anything by 1. And so it'd be on the first coordinate. If it was on iteration 31, 31 mod 2 is 1, +1 is 2. So it'd be on the second coordinate. And it's just looping through these. And what it's doing is you're basically minimizing a function in this direction, and then you're going in the other direction, and then the other direction, and the other direction. But you're always sort of going along these coordinate axes. And a special case is when you choose your step size, choose eta t, such that wt plus 1 in this ith direction is equal to argmin w f of wt plus the direction Okay, and so what it's doing is it's picking that step size in the direction of the ith dimension to minimize that function. And so instead of doing this sort of just like random steps, this special case will actually be minimizing the function. So if I start right here, I might go to here, and then here, and then here. Okay, this is a bad example because it's not exactly looking like it's converging faster, but it is. And it'll get to the minima a little faster. And so you're going to have some practice with this. How your homework is going to be is that you're going to optimize lasso using coordinate descent. And it's basically trading off these different dimensions, you're optimizing basically one dimension at a time. Okay, why is that nice? Because, you know, just looking at these functions, a lot of the time functions are very, very simple along a single dimension. And we can go straight to the minima. And we have closed form solutions for what that minima is. And that's exactly what happens with lasso. Minimizing a convex function along one dimension is sometimes very, very easy, leaving all the other coordinates fixed. But optimizing all the coordinates in the same time, there is no closed form solution. And so you'll see an example of this on the homework for lasso. The algorithm is there. And I encourage you to look in the book for the derivation of that algorithm. But it's essentially performing coordinate descent, changing one at a time. And because we're convex, we are guaranteed to converge to a global minima. And this is just another example that I want to highlight of why convexity is so important. Because doing something like this, like these greedy sort of approaches, they're sort of clever computationally, are always guaranteed to converge to a global minimum. And this is why we like it. This is why convexity is so important. Yeah, and that's why we harp on it. Yujit, you have a question?
Hello. I have a quick question. So, for example, if a function is not differentiable, can we smooth that function somehow and then use the gradient descent with the gradient?
Well, it depends what you mean by smooth. Yes and no. So you can't just add like a quadratic to it because the function would still be not differentiable. However, if I, for the physicists in the room, if I convolved that function with a smooth function, that would effectively be smoothing it. So if you convolve sort of a continuous function, like a Gaussian sort of bump, with any convex but not differentiable point, that function will immediately be infinitely differentiable, which is kind of an amazing fact. So yes, if you have any non-convex function, you can always smooth it by convolving it with a Gaussian. That's a nice sort of math trick, but practically that's much more difficult to do than say. How would you actually do that convolution? I don't know. But there are very nice tricks with using randomness to do the smoothing implicitly, but that's way beyond the topics of this course.
Thank you.
So, as Jamie went into last time, we're finally getting to our topic sort of today, but I wanted everyone to have that background of convexity, of like having these deep sort of intuition for what is a convex function, how to prove it is convex, and why we care. And so because the problems that we look at, we get data sets. Yeah, we get data sets that look like this, xi, yi pairs, where xi's are features, yi's are labels. And then we define some loss functions over that data set. This could be squared loss or hinge loss or logistic loss. We've seen examples of all of these. And then our gradient descent is then, we define the loss function as the sum of all these losses. And if each loss Li is convex, then the sum of all the losses are convex. And so what we have is then that the gradient of this is just the gradient of this guy, and then this is just equal to Wt minus eta grad W. Oops. The gradient can come inside. And then we can define our update, where for each one of these loss functions, now we're taking the gradient of just each individual Li, which is very, very simple. We can compute these very easily, and we do our gradient descent algorithm. Okay. And so if each is convex, the sum is convex. And this property is what makes gradient descent work. Or not work, but it allows us to be very confident in that if we run this gradient descent algorithm, we will be able to get to a global optimum. We don't care how the algorithm does it. And that's critical here. Use any step size you want. You initialize anywhere. If the function is convex and you run gradient descent with a small enough step size, you will converge to the global optima, and you can tune that step size to converge as fast as possible. But if you're doing something non-convex, that's not necessarily true. You'll converge a local minima. You'll never know it. Testing if a function is at a local minima can be actually NP hard if the function is non-convex, which is a terrifying fact. So the takeaway here is you can always run gradient descent whether it's convex or not, but you only have guarantees if it's convex, and that's why I like convexity. There are many solvers for convex problems. If you know your function is convex, CVX is a software package for convex optimization, and it's very fast for specific optimization problems. And you can add constraints saying, you don't want to optimize over all the real numbers, but over like I need x1 to be greater than x2, these sorts of things. And so this is a very, very big field. We just talked about gradient descent. Many bells and whistles can be added to gradient descent. We'll see later in the quarter when we talk about neural networks that you'll see optimizers in Torch or these packages that look like that utilize these bells and whistles often, like necessary accelerated method, Adagrad, Atom, etc. And all of these functions are really just well, in particular, Atom is really just modifying the step size. Adagrad and Atom are really just, instead of having a single step size for every dimension, it has a different step size for each dimension. And in practice, this can result in a huge win, even though, and theoretically, you can also prove that it works better.
The question.
Okay. Yeah.
So we were talking about, convex functions and sets, but how do you deal with a non-convex function where you're at a local minimum but you want to get to a global minimum?
Yeah, great question. If we had the answer to that, we would
maybe win a Turing Award.
Yeah. Yeah, no, this is one of the biggest problems in machine learning right now, and in optimization in general. Which is like if you have a non-convex function and it's high dimensional, meaning you can't see it,
right?
Like you can't visualize it. It's computationally hard, and you can prove that it's NP hard to actually even test if you're at a local minima. This is not testing whether you're at a global minima. I'm saying if you've converged to something, just to test whether you're at a local minima, meaning are you at? So this is a function f. The gradient so this is like, this function is like x cubed, right? It goes up and it goes through. At x equals 0, f prime of x is equal to 0 at x equals 0. Right? That gradient's 0. You're not at a local minima though. Right? You are actually at a saddle point. And this is a very easy function, but if I give you a quartic, actually, you can prove that it's NP hard to test. I'll give you a point, and to test whether you're at a local minima or just a stationary point, like a saddle point like this, it is extremely difficult. And you just basically have to try everything, looking at all 2 to the d dimensions, all 2 to the d sort of locations or exponential dimensions, more than that. And it's just very, very hard. And so like, this is just deciding between a saddle point or a stationary point and a local minima. If you're at a local minima and you're trying to decide whether you're at a local minima or a global minima, that's an even harder problem.
Yeah.
That's just sort of like intractable. That's just like, no, you have to look everywhere to be able to test that. And it's we just don't know how. If you're at a local minima, escaping from that local minima is very hard to try to get that global minima. And so there are other tricks like adding noise, and other sort of heuristics like using momentum and things.
Or random restart if you've started somewhere and yeah.
Yes, random initialization is a big one. So you start your optimization process, you get to a minima, then you randomly initialize it again, and then go to a minima again. And you just hope that you're getting to the global minima. And in general, you don't know.
Could varying the step sizes help with that?
Yep.
Okay.
Yep, the step size matters.
Actually,
Everything matters.
okay.
We don't have a good answer for it. It's one of the biggest challenges in machine learning right now.
And then I just had a clarification question on the last slide, just what T+1 means.
Oh, T iterate. So T is iteration
Okay.
T.
Got it.
In the algorithm that is gradient descent.
Oh, I see. Cool. Thank you.
Okay. So what we're going to talk about today, is something called stochastic gradient descent. And this is getting to this question of computation. So in machine learning, we have these problems of we have this data, we get a bunch of loss functions, we take the gradient, and we have something that looks like this. And again, I'll just rewrite this out. Now, that's fine. But what if n is large? Like, what if n is equal to 10 to the 8? Okay, we're using census data, and we have a data point for each person in the United States, right? And we want to know, like, they're averaging their ages, or like finding the median age. That's a convex optimization problem that doesn't have a closed form solution. How would you do that? I mean, like, it's kind of intuitive that if I'm looking at 100 million people and I want to find their median age, like if I look at a random sample of that median, if I say sample 1,000 people and compute that median, that's probably going to be pretty close to the true median, right? It's going to be an approximation, but it's going to be pretty close. And so there is this sort of notion of sampling and the fact that, like, I don't need to look at every data point to be able to get to a solution that's pretty good, that's pretty useful in that it gets to an approximate local minima of this problem. Because how you should think about machine learning is that you're always going to be solving it with a gradient descent type algorithm. And when we throw pictures like this, where like it's getting to the minima here, that's actually kind of a lie. We almost never actually get to the bottom of the bowl. We usually stop the process early. We're almost at the minimum because the gradient, because progress, one of the properties of a convex function, and really any local minima in a localized neighborhood, even for non-convex functions, is that the gradient gets smaller as we get closer to the minimum. That means you make less and less progress getting the distance. You make less progress towards the distance to the minima as you get closer to it. And so it's actually possible that you never actually get to that minimum. You stop early. And so turning this sort of on its head, if you know that, if you know you're never actually going to get to the bottom, then maybe you actually don't need to get to you don't need to find this function value. You just need to get in this localized neighborhood. And that means you can have a little error tolerance. Maybe you can optimize a simpler function and only sort of approximately minimize it. And you sample some, you optimize some potentially different function that's a sampled version of it that was a little different, but you actually minimize that function, or maybe up to a factor of 2. Then what you can say is that, like, well, I solved this much, much easier problem and my error tolerance is about the same. And so I don't really care. I got to the answer much, much faster. And so what we can use is the probabilistic method to actually achieve this according to sampling from this distribution. So What I mean by that is if I had 100,000 people or 100 million people, and they all had their own loss function, and I wanted to do the gradient of all of them, what I can do is I can do a thing called stochastic gradient descent. And how this works is I'm not going to each step of my iteration process, WT plus 1 is equal to WT minus the gradient over all data points. I'm just going to select one of my loss functions uniformly at random. Okay? I know IT is going to be an index. It's in 1 to n. I have n functions here, and n data points, say. I'm going to draw one uniformly at random, take the gradient of it, and then do that gradient step. Okay, so instead of doing n and averaging them all together, I'm going to do just 1. And now it's pretty easy to see that this expectation of this guy, well, what is this expectation equal to? It's equal to over all possible values that IT can take, the probability that IT is equal to I times the gradient of Li of W. But then the probability IT was drawn uniformly at random from 1 to n. So then that's equal, each one of these guys is equal to 1 over n. And then we get that the expected gradient is equal to the true gradient. Right? The expected gradient of this loss function, IT is the randomness here. IT is a index, uniformly at random drawn from it. And what I'm saying is the expected gradient over all the data that I could have seen is equal to the true gradient, because the true gradient is this guy. And so in expectation, if we do this stochastic gradient, if we draw some data point and then we perform this update, the direction that we're in expectation is equal to the true gradient. But the difference here is that to compute the full gradient, do the full gradient update, that's an order n operation. I need to sum n things together. I need to take n gradients, and then I need to sum them all together. Whereas with this guy, the stochastic gradient, I'm only taking, I don't need to do that. I'm just sampling some point uniformly at random from 1 to n, and then evaluating it, taking its gradient, and then doing the updates. So it's an order 1 operation. So it's much, much more efficient, takes order n less energy, right? Less computation. Okay. But the difference, it's only an expectation, right? So if we had some nice function, the picture in your head should be like, let's say this is L of W. Then if I'm at this point, the true gradient, the true negative gradient is, say, this value. So this is negative grad L of W. This is W. That's the true gradient. But at any given time, for different indices, the random gradient, Li of t, this guy, based on the IT, it could be this way. It could be this way. It could be this way. It could be all over the place. It could be in any direction, in fact. But what we do have is that an expectation is going in the right direction. In an expectation, if I draw many of these and I average them all together, they will sum up, or they will average out to the direction of the true gradient. And so when I run any, if I start this procedure at this point, I may have, this could be W1, And then on the first iteration, I can actually go up, right? That can happen. But then like maybe then I go back down, and then I go back down. I'm making a lot of progress, and I go up, and then I screw up, and I go back, and I go back down, and I go back down, and I go up again, because these are all stochastic gradients, and then I eventually sort of get my way down to the bottom. But what you should think about here is that while gradient descent is this very sort of controlled process, it's almost like this nice damp process which is going downhill. It's a ball sort of rolling downhill. It's very nice and smooth. Think of like how gravity would act on a ball, very smooth. The stochastic gradient descent is still going in the general direction, but at any given time, it could be going up or it could be going down. And it's very sort of erratic. But so there's a lot of noise in the gradient, is what we like to say, is that it's generally going in the right direction, but in any particular step, you could be going up or you could be going down. Okay? And so that is stochastic gradient descent, where we would, at each time, we would draw an index uniform at random from 1 to n, perform, evaluate the gradient just on that one index, and take a step in that direction. This is extremely computationally efficient because we're not taking the gradient of all endpoints at each iteration. We're just taking the gradient of a single point at each iteration. And the price we're paying for this is a little bit more variance in our estimates of the gradient. Any questions on this?
Relating this back to like one of the homework assignments that we did, could we use like something like Hofting or something to kind of like calculate the M that we need or something to get, you know?
Yeah. Hold
like
that question for a moment. I'll come back to that. So I'm not going to prove this theorem to you, but I just want to sort of, I wanted to show you that you can prove things about this. You can actually show that if you run this algorithm, because with the gradient descent algorithm in the noiseless version, it's pretty obvious that it's going to converge just by picture, proof by picture. And so stochastic gradient descent is not as obvious. But in fact, you can show that if for these loss functions that are convex, if you define some parameters, say like your starting location is if your starting location is not so far away from, or distance r from your end location, if your gradients are bounded, meaning like the largest value your gradient can take is bounded, then basically with the right step size choice, you can prove that the expected loss, the deviation away from the truth, is going down like 1 over root t after big T iterations. And so this is kind of a remarkable fact. All I used here was that L is convex. And what we were able to show is this very, very general result that it's going down like 1 over root t, which is actually pretty slow. If you wanted to get an epsilon error where epsilon is 0.01, t is going to be on, have to be on the order of say like 10,000. So you're going to need a lot of iterations. And this is sort of like one of the trade-offs here. Usually for gradient descent, the gradient descent typically converges like e to the minus t, whereas SGD typically converges like 1 over t or 1 over square root of t, which is way, 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 way slower. And this is the trade-off. That if you're running gradient descent, it's going to take you way, way fewer steps, fewer iterations, but way smaller cost per iteration, right? Because gradient descent, while it's converging like e to the minus t, so to get an epsilon solution, you might only need log 1 over epsilon iterations. But if you have to, if your loss function looks like this, then that's n computations per iteration, versus stochastic gradient descent was just one computation per second. So what that means is that the total amount of compute, total amount of flops, floating point operations, arithmetic operations, is going to be something like n times log 1 over epsilon to reach epsilon good solution. Is like n log 1 over epsilon, whereas for stochastic gradient descent, it's more like 1 over epsilon or 1 over epsilon squared. And so the big point here is that this guy, independent of n. So if n is very, very, very large, you can start making progress before you've touched every data point. And in fact, this is very real. So if you're training some big image classifier or something like this, where you have literally hundreds of millions of images, or training a language translation model where you have just uncountably any of translation examples, n is enormously large. And so while you may want to look at, do multiple passes over that data set, you will want to, you don't want to have to make too many multiple passes over the data set. You want to be making progress way before that time. And this is why stochastic gradient descent is so amazing. It is independent. Its performance is independent of the number of data samples that you have. It will make progress regardless of how many samples you've looked at, which is its really remarkable property. It's really a computation thing. It's not having to compute that n-dimensional thing. Any questions?
Yeah, I have a clarification question. So what is the epsilon in here?
What is what?
The epsilon here.
Epsilon, oh, so this is an epsilon good solution.
Okay.
So it means that f of wt minus f of w star is less than or equal to epsilon.
Got it. Thank you.
Okay. I'm not going to go through the proof, but I wanted to put it here just so you can look at it for those that are inclined to go through it. Why I wanted to put it on here is because it's so simple. It fits on one slide. The proof of this result, and it actually gets into how this actually works. And so the big step here is the stochastic gradient step. But here you're using convexity. It's really the only place you're using convexity, and it's just really a remarkable result. So I'm not going to go through this, of course, but for those that are interested, I strongly encourage you to go through it because it's interesting. Slides are up there on the website. Okay, so back to the question that was just asked a moment ago. Well, we know this thing called tufting. What we could do on each, if each one gradient is some stochastic realization that only an expectation is going to be in the direction of the true gradient, what if we average many stochastic gradients together? So not all of them. You don't do all of the n gradients, but you do some batch B. So you take B random indices, not just one, but B of them, and average those together. Then that stochastic gradient is going to have less variance. And you'll also get concentration. And so you can apply something like Hufting's inequality in a particular way, not exactly to the gradient directly, but you can apply Hufting's inequality. But by averaging many gradients together, you are reducing the variance of the gradient and making it less noisy. And that can, in turn, accelerate the convergence a little bit. However, and it's a big however here, for convex functions, there's pretty limited theoretical motivation for this. You're really just changing constants around, like a factor of 2 or 3 it's really not actually that valuable for convex. But as we were just talking about for non-convex functions, someone brought up step size. Is step size a big factor? Absolutely. The initialization is a big factor. The amount of averaging that you do is also a huge factor, because what you can do if your batch size is too small, there's a lot of noise in your gradient, and that can actually help you. Having noise in your gradients can actually help you escape those local minima and those saddle points, because there's so much noise, they'll just randomly knock you out of it if it's a sharp minimum, which would be great. But as we get a larger and larger batch size, it's converging sort of the true gradient, and you're more susceptible to getting caught in that local minimum and with a non-convex function. But there's trade-offs here. Why would we not just want to use the smallest gradient? Why would we not want to use batch size 1? For many reasons. There's computational trade-offs here, because if you're computing B gradients at a time and performing those updates, well, that's actually relating back to our first slide. That first slide, depending on how you do it, if you look at the slide, if you compute each gradient at a time and then do a for loop, yeah, it's going to be slow. It's going to be bad. But if you compute each gradient in that batch and you use matrix operations on those to do the updates, to do these very fast, you're using the full power of linear algebra and LAPACK and BLAST and all of these operations of linear algebra that have been optimized to death in your computer, you can get a substantial savings to the point that you're actually getting it almost for free. And this is the power of, and then the other advantage of this is parallelization. If I have a GPU, gradient descent is inherently a sequential process, right? I take WT, WT plus 1, WT plus 2, etc. But we want to parallelize this algorithm. We have GPUs, we have other computers. You want to use parallel computing to be able to help this. And one way to use parallelization is for data parallelization. I break up into batches, send compute batches, compute gradients by sending a partition of the batch to each computer. Or in the world of GPUs, each core of that GPU. And this is what has, it is not an exaggeration to say the boom in deep learning and artificial intelligence the last 10 years is really thanks to this last piece of parallelization and GPUs. Making these these matrix factors, it's actually both of these things. Fast matrix computations, very efficient on GPUs in a parallel way, is what enabled us to train very, very advanced large models very, very fast. And it's SGD is responsible for that. And SGD is everywhere. It's not a new algorithm. It's been around for everywhere. So like your phone, you walk around, this phone is constantly pinging the cell tower, constantly trying to learn, because it's multipath. It's bouncing off the walls, it's bouncing off the trees, it's bouncing off buildings, and it needs to account for that. And how it's doing that is through an algorithm called LMS, linear least mean squares, and that is essentially just stochastic gradient descent. It's been invented over and over, and it's trying to fit sort of like what you're doing. If you've ever done dial-up, if you ever had that really noisy, ugly sound, that is doing stochastic gradient descent actually. It's sending a signal, a probing signal, it's getting some loss back, it's running SGD steps constantly, and then it's finding the channel, because phone lines are inherently horrible. And that's how you can actually communicate over the internet. It's just amazing. SGD is everywhere. It's the reason the internet works, and why telecommunication works, but it's also the reason why artificial intelligence works. Its importance to our everyday life cannot be overstated. This small little change is extremely important. Okay. There's also a different perspective on scatter gradient descent, but I'm not going to go through it. We already sort of, I'd encourage you to go over these slides, but it's not that important for our purposes. And so again, how would I, so the last thing I want to talk about is I'm doing a stochastic gradient descent. If I look at this, I'm not even going to do this at all. I'm not going to do batches like this. What I can do is I never need to instantialize either the H matrix or the H transpose H for any size. What I can do, I can actually make this. What we just proved was that I can do this because this is just doing least squares, right? It's just doing least squares. So what I can do is I can say WT plus 1 is equal to WT minus eta times the gradient of, I sample some IT of YIT minus XIT, or sorry, HJT of XIT squared, where I've sampled JT is uniformly at random from all my functions, IT is uniformly at random from all my points, and it will run. What is the memory computation of this? This is, well, if I loaded this into memory, that's n times d. But then to compute this is just p dimensional. It's just p. And so we went down from, we started with something that was nd plus p squared plus n times p. And we got down to something that's just nd plus p. Really quite amazing. And so this is really what I want to really emphasize. Actually, we need to store the g. So that's p times d, but not p squared. We avoided p squared because p can be in the tens of thousands, d can be like 10. So p squared is what really killed us. And we were able to do this computation extremely efficiently. And this is the power of stochastic gradient descent. And if you actually ran this, it would be very, very efficient. That's all I wanted to say today. And so you'll be running gradient descent, stochastic gradient descent on your homework. This will lead us into our story on deep learning later in the quarter. Okay, thank you.
And the homework will be up shortly, sometime later this morning or early afternoon.
Okay, so you're all free. Saving some questions, some good questions. How do you choose the batch size B? That's a good question. It's a hyperparameter. You have to choose it for non-convex optimization. It really it's just like a step size. It could make it it will actually result in a different solution at the end of the day. Different step size, different batch, you'll fall in different local minima. But even for convex functions, it's not obvious how you just pick the batch size. And that's what you'll investigate on your homework. Choosing step size and the batch size, these are parameters that you need to optimize to get as fast to the minima as possible. And usually this takes some hand tuning, or you don't even try and you just sort of pick a value that seems reasonable. Or as big, if it's convex, you can fit basically the biggest value of B such that you can fit it into memory. Is often a good size because that's per step. And so if you can do all of that computation per step without slowing down, just in parallelization, you should do that. Yao, you have a hand?
Yeah, I have two questions related to the stochastic gradient descent. So the first one is about how do you choose a batch? Because to my understanding, is you said like to choose a batch, we just randomly subsample some from the training data set. And then I just have a question. Is it possible for us to not, well, I think it's just a problem with randomly sample some from the whole training data set. Do you think it's possible that we will miss some of the data from the training data set, especially when sometimes we have a budget limits in how many iterations we can do? Well, it'd be better if we just chunk the whole training data set like into, for example, 500 chunks, and we just iterate all those instead of doing a totally stochastic one.
Okay, you brought up or touched upon a couple of extremely important points. So let's start at the top. Even without gradient descent, if I wanted to do, stochastic gradient descent is, choosing an IT uniformly at random and then going like this. In practice, I actually don't recommend this algorithm. In practice, what's a little bit better is to choose, if we define an epoch to be n steps, so if you have n data samples, that'd be one pass to your data. What it actually works better, almost always, not provably better, but almost always in practice, is to choose a random permutation of your n data samples and then walk through that permutation